your previous lesson?
No.
No. Okay. Hi, you're here for dynamics and stochastic processes. I am Sohal. I'm now in my 4th year in the SAT, I think. And I'm a student of Eddie Menken and Nadim Mizrahi. I do experimental work, but also some computational work, which is actually heavily based on material that is taught in this course. I am your teaching assistant in this course, which means that I'm giving all the lectures, writing the exercises, checking the exercises, writing the exam, and checking the exam. And you will not have contact with the supervising professor, Thompson Polinsky. His job here is to basically he builds the course. He gives advice about what material is taught and stuff like that. So everything is, all the interaction is with me. Another thing that I'd like you to know, I made a sheet with the technical details of the course, so I forgot to print it and hand it out, so it will be on the Moodle. I want to show it to you now on the screen. I don't know if you know, but ThinkPads don't always recover complete. It's a well-known problem. Okay, I'll start anyway. In this course, we will have 6 exercises, one exercise each every 2 weeks or so. There will be one small project that is kind of, the scope should be just a little more than an exercise. The scope of this project. Probably you will get time to work on it during Passover, where we will miss 3 consecutive lectures, and then we will have time. What else? All of the course is given in English. All the exercises should be written in English, and the exam will be written in English. Okay? There is no Hebrew in this course. you are not required to follow the course in the book. Okay, it's optional. In the Moodle, you will see for each week the recommended reading in the book. And basically, I hope that you will be able to understand everything without consulting the book. I hope to cover everything myself. So that's not a requirement. Okay, here you can see my email. I also use my Gmail, but so it doesn't matter which one you send to because they all go to the same inbox. Reception hours. If you need any help about the exercises or understanding things that were covered in the course, then you can come to me after class on Wednesdays. If there is a problem with an exercise that you are required to submit on that day and you need some help, then you'll get an extension. I'm not very strict about the deadline about the exercise, so if you have, if you're busy, if you have a lot of stress or any personal reasons, then you will probably get an extension if you will ask for it. The only thing that I can't do is give you an extension for after the exercises are returned to the class. Okay, so there is a syllabus here. I'll go over that in a minute. Final grade is based mostly on the exam, 70%. Also, I don't care if you turn in a hard copy or a file to my inbox, okay? I don't mind. If you turn in a file, I will return a file with my comments and grades on it. Although some of the requirements, some of the questions in the exercises will require you to draw some plots by hand. So if there is things that you need to draw by hand, then you should maybe scan it and then send it. Okay, I prefer that you do that rather than make graphs on a computer. Also, when you solve the exercises, it's very important to keep to the standards of academic work, which includes labeling of the axes. Every year, students forget to label their axes. You can't give me a plot where I don't know what the axes mean. Any physical quantities must carry the unit in your calculation. There's no sense in saying that the time is 5. Okay. Time has units. Now for the syllabus of the course. We have two parts in the course, dynamics and stochastic processes. Dynamics will occupy about 3/4 of the course. This is the main topic that we cover. And stochastic processes will be 3 or 4 lessons at the end of the semester. I think this is it. A lot of the exercises, a lot of the work in the course will require some programming. So you will need to use MATLAB, or if you want other languages, but MATLAB is very convenient for what we did. So if you don't have a good knowledge of MATLAB, then you will have to catch up. I can help you a little, but I don't have a lot of time. Let's turn off the projector.
So,
yeah.
Could you use the microphone? Because otherwise
Yes,
I can't
I
really
was
hear you.
meaning to take the microphone. in the second lesson, I will pass a sheet between you because they want to have some, to know some things about you, like what's your background, how much you know MATLAB, okay? And let's just see if we'll do a short round. Each one, please tell me your name and your background. Okay. Physics, biology, whatever.
My name is Guy. I studied mathematics for my bachelor's degree, and now I'm studying my master's in neurobiology.
Okay.
My name is Gal, and I did my bachelor's in economics and history.
Mm-hmm.
Shai, psychology major.
Psychology? Cognition? Okay.
My name is Nora. I studied a little bit of applied physics and a little bit of MATLAB Foundation.
Okay.
Lial, math and linguistics, and I did computer science.
Okay. The name again?
Lial.
Yeah. Okay. You?
Hi, I'm Lily. I studied economics.
Mm-hmm.
I know good enough.
Okay.
Chen, science, computer science.
I'm Hagar, I studied physics and biology.
Okay, Rohan?
I am Ronen, cognition and psychology.
Shai, chemistry and biology, and I'm fine with MATLAB.
Okay. I'm also a chemist. I have a master's in chemistry and antibodies.
Yochel, I studied computer and cognition, computers and cognition, and antibodies.
Daniela, I also studied computer science and cognitive science, and I'm fine with math.
Okay.
Yeah, studied electrical engineering, and I'm fine with math.
I'm Alex. I studied mathematics and algorithm engineering.
Carmel, physics and philosophy, and I'm my final year in the bachelor's.
Okay.
Me, biology and cognitive science, a bit of computer science, and I don't know. Depends on the MATLAB requirements.
Okay.
Yeah, I'm fairly okay with everything.
Okay.
Tachel, also did my bachelor in chemistry and physics. Now master's in brain and behavioral science.
Okay.
Roni, physics oceanography, completed.
Okay.
Hadal, my bachelor was in engineering, physical oceanography, and that's fine with me.
Yochel, biology and cognition, doing PhD in neurobiology.
Okay. So I see here a lot more people than were registered on the meeting. So, right?
Yeah, I'm not registered.
Yeah. Okay. I hope you'll stay with us. Okay, this covered all the technical stuff. And today we're going to start with the topic of dynamics. Right? Now, dynamics is a field. Today you could say that it is a field of science, or maybe an area of mathematics. But don't be afraid. The tools that we use here are quite simple mathematical tools. What we are concerned here with, oh, I forgot. I think the microphone was not. It's not working. All the lectures are videotaped, so you can see them on the Outlook website.
Yeah, usually it's better if you use the microphone. So
yeah, I know. This is why I'm trying to see what happened to it. You can hear me? Okay. I don't know what I did. Okay, So you can hear me through the microphone? Good. So in dynamical systems, we are interested in systems that undergo change. And we are interested in systems that evolve with time, and especially with those systems that it is hard to describe mathematically, which means a lot of times we know what the forces acting in the system are, so we know how the system should evolve from one point in time to the next. But it will be very hard for us to write some expression of the state of the system at each point in time. Okay, so you might know systems from physics, from mechanics. For example, the pendulum. And the way we treat the pendulum is we say, okay, the movement of the pendulum is in small angles, so we will approximate it, and then we have an expression where the pendulum is moving according to a sine wave or something like that. But this is only an approximation. So what if we want to describe the movement of the pendulum not only in small angles? This is already harder. And dynamics gives us some tools to do this. Historically, the need for this arose after Newton was extremely successful with his laws of motion, so he could describe the motion of planets quite well. Okay, so if you consider the sun and the Earth, then you can write equations for the orbit of the Earth around the sun and know where it is at any time in the year. But when you try to introduce another planet or the moon into the system, this is already very difficult. So people tried a lot to solve the system, the three-body problem. And during the 19th century, it was found out that this is actually not possible to solve analytically. And it seemed like a dead end. But in the 1880s, Henri Poincaré published a series of papers that introduced new tools to study such systems, such complex systems. And and these tools were actually, what he did was giving up the desire to know everything quantitatively about the system. So he was applying mathematical tools in order to say qualitative things about the complex system. This is what we'll do in this course. Basically, we would like to take a complex system, and even if we don't know exactly what will happen in each point in time, okay, we can simulate it using a computer program. But if we, even without simulating, we'd like to say, is this system stable, okay? Is the solar system stable, or are planets going to descend into the sun or run off into space? This is the type of questions that we want to ask. And so Poincaré's tools made a revolution in this field, and the next revolution came when computers became available. And then we could actually simulate everything. This started in the 1950s, and pretty quickly, already in 1963, Edward Lorenz published his seminal paper that described atmospheric convection flows and basically described for the first time the subject of chaos. And chaos is also something that we will touch in this course. Okay, so the way we describe the systems in our course is this. We use differential equations. Okay, you might have heard of differential equations. So in this course, we will usually not solve the differential equations that we write, and we will try to say things about them without solving. So a differential equation, we will describe it in such a general form. This thing that looks like a variable, x, is what we want to find. This is our unknown. And this is not actually, it's not a constant variable. This is actually a function of time. So we are looking for a function, x of t. The state of our dynamical system is described by x, and it evolves with time, and it can, of course, be composed of several different variables. Okay, so we could have x1, x2, and so on and so on. And in short, we can write this as a vector. Okay, this is my notation for vector. And in principle, I can do this and describe a two-dimensional, three-dimensional system or more. So this is a bit about the conventions. In this course, we will almost always differentiate by time. Okay, so we will just write x dot. This is just a notation for dx over dt. What else? Don't be confused with other notations. Okay, so x dot is only differentiation by time. Okay, so the most basic categories that we deal with in our field will be differential equations and difference equations. And the difference between these two things is that here we are talking about continuous time, and here we are talking about discrete time. So this will be like I wrote with this general form, and here we have xn plus 1 equals a function of x of n. Most of what we do will concern differential equations, and we will touch on difference equations in the end of the dynamic section of the course. Now, in the differential equations, we further divide them into linear and nonlinear. I'll go over these definitions later today. So these are quite simple to deal with, but it's useful to study them a bit, even in this course, in order to know what to do with the nonlinear equations. Basically, what we do with the linear equations is the basis for the way we treat the nonlinear equations. We do linearizations around certain points in the system. And since we know what to do with this, then we kind of approximate the nonlinear equations. Nonlinear equations will deal with cases where you have interactions between components in the system. For example, competition or cooperation. We'll see this in models of populations that we will look at. Okay, so other than these properties, another important property of the systems that we will see is the dimension of the system. I already showed you here that we can have several variables describing the system. So the dimension is just the number of variables that we need to describe the system, to make predictions about the system. And the dimension is critical in determining which properties arise in our systems. Okay, so I can make a table with a dimension. I'll give you some examples just so you'll know, what we are going to deal with, or actually how wide is the scope of dynamics and the tools that it gives us. So with one dimension, this is usually models of exponential growth. For example, populations. It's more applicable to populations of bacteria. Decay. So radioactive decay, for example. What? Say again? A free fall?
Yeah, like my speed compared to where I am.
Well, no. So the laws of motion have a second derivative, and the way we treat the second derivative here is by adding a dimension to the system. So we have two dimensions. One is the displacement, and the other is the velocity. And so this will be in the second dimension. Okay, an RC circuit is also something you can describe here. And phenomena that we encounter already in the first dimension is, growth, decay, but it's not always this. It's you can have stable equilibrium. Okay, decay is into stable equilibrium. These are things that we will see today, even. Later in the course, we will go into the second dimension, and this will be basically the bulk of the material in the course, is dynamics in two dimensions. Here we will have RLC circuits. Well, we won't do them ourselves, but RLC circuits belong to the second dimension. Simple neurons. Sometimes a model of a single neuron is simplified by making some assumptions, and you can treat it as a two-dimensional system. We'll have this in one of our exercises. And for example, predator-prey systems in population models. And here you will see the type of interaction that gives us nonlinearity, for example. Yeah. Yeah. Sure. Now, when we increase the dimension from 1 to 2, we already get phenomena that were impossible in the first dimension. So these are oscillations. And a special type of oscillation called the limit cycle, which is very interesting for people doing neuroscience because it can describe, for example, spontaneous spiking of a neuron. Okay. So from the third dimension and on, things get very complicated, and most systems are impossible to solve analytically, and even very, very hard to predict. Here we are talking about neurons. So for example, the Hodgkin-Huxley model that you probably saw in the first semester, if you're in the ICNC, it's a magnificent example of a model in dynamics that actually makes predictions on reality, and it's in several dimensions. Chemical kinetics. So some people study chaos in chemical systems. In atmospheric models, sometimes they can be simplified, like Lorenz's model, to 3 dimensions. So from the 3rd dimension and on, we start getting phenomena that belong to the field of chaos, like strange attractors, fractals. We will see some things about chaos in this course, but one of the points about chaos is that once you have a chaotic system, there's not too much you can say about it. And very large dimensions will have examples like neural networks, where each cell's firing rate, for example, can be a dimension of the system. Ecosystems and economics, things that usually you will have to simulate in order to make predictions. What people do, for example, with neural networks is a lot of time to reduce the dimensionality and do mean field models and go to n equals 2. Right, so this is a kind of overview. In the course, we will start today and probably also the next lesson with n equals 1. Then we'll spend some lessons on n equals 2. And finally, we'll have 1 or 2 lessons about chaos. And then we go into the stochastic section of the course. Yeah, also important to say, everything we do here in these dynamical systems is deterministic. So we will see complex behaviors that arise from the inherent properties of the system, not from noise or not from anything stochastic. Everything is deterministic. And what we call chaos, also it's a little confusing, but it's systems that are perfectly predictable if you know the initial conditions. The problem is knowing the initial conditions and the fact that the initial conditions have a very strong effect on the result. Yeah?
Does the dimension, the number n, does it represent the number of parameters that are known in the system? This is what the definition is?
Yeah, basically, yeah. The number of variables that vary with time.
Which are unknown, and you can play with it.
What?
And you can play or change the parameters.
Yeah, so we make a distinction between variables and parameters. Right? So the parameters are things that you consider as constants, for example, the constant of gravity or other physical constants. So for your needs, the parameters are constant, and this represents the variables that change with time. Yeah, you can take a one-dimensional system with a parameter, we'll see that, and vary the parameter with time. So actually you have a two-dimensional system, but you would like the time scales to be different.
So essentially, is that n equivalent to that n with vector x?
Yes. Okay, we'll start. Just a reminder of differential equations. Some definitions. Okay, things that you should know about a differential equation that you're given is first the order of the differential equation. This is the highest derivative that appears in the equation. Okay, so when I write this is the first order equation. because I only have the first derivative. First derivative, dx over dt. If I have such an equation, this is already a second order equation, where this represents, this is a second derivative with respect to time, x 2 dots. This is a standard way of writing differential equations. You just group all the components with the dependent variable x and its derivatives into one side, and you have either a 0 or a certain number on the other side. Another property that is interesting for us is linearity. So an equation is linear if it only includes the power of 1. Okay, so your variable can only appear to the first power. This is linear, right? This is not a linear equation because we have here a second power. Also, trigonometric functions, exponents, logarithms, they make nonlinear equations. Okay. Okay. An autonomous equation has no dependence of the derivative, no explicit dependence on t, or on the independent variable. So, to give some examples, this is autonomous these are non-autonomous. The independent variable t can multiply the dependent variable. It can come in an addition. These are non-autonomous.
So the way we should write it is like f of x and t, right? It gets
yes. So yes. So this will be x dot equals f of x and t. Yeah. A non-autonomous equation can be linear. Okay, if you have this equation is linear. This is linear, according to our definition. X dot equals 3x times t plus 4t plus e to the power of t. It's still a linear differential equation. X dot equals e to the power of xt. This is not linear, obviously. It's not linear in x. Another property of differential equations that we'd like to know about. Are actually not very relevant for us in this course, but still good to know. Homogeneity. in a homogeneous equation, you have no term that is not a function of x, of the dependent variable. So this is a homogeneous equation, and if you have some, let's write b, some number b, this is f of x. This is a non-homogeneous equation. This comes into play when you try to solve your differential equations. But what?
Is the difference between is the first one 0?
0 and a number. Okay. Okay. We will not be solving usually the equations, so I will not give you here methods of solving differential equations except for one. And this method is, there are many methods of solving differential equations, and each method applies to different types of equations. And what we are going to see here is separation of variables. I guess all of you have already encountered this. When we are dealing with autonomous equations, as you will see, where there is no dependence on t, our equation is always separable. So the general form of a separable equation is dx over dt equals f of x times g of t. So in an autonomous equation, g of t will always be 1, and then we can separate. What we do for the separation of variables is we try to group everything that depends on x on one side and everything that depends on t on the other side. In our case, it will be very, very easy. Basically, what we do is this. We divide by f of x, and we multiply by dt. And then we can integrate, hopefully. Two things that we need to remember. The first one is always note the conditions where f of x equals 0, because you want to divide by f of x. It's a bit trivial here, because then you will have no dynamics if f of x equals 0. So if f of x equals 0, then dx of dt equals 0, and there is no change in the system. But this is interesting. The points where this happens are interesting, and we will go into them. Another thing that you must always remember is that when you integrate and you have no explicit bounds, you must write a constant of the integration. So we'll see this in an example. Take this equation, x dot equals 1 minus x over 2. So I can write this as dx over dt, and I'd like to separate the variables. So I divide by 1 over x, by 1 minus s, and I note on the side that x does not equal 1 for my solution to be valid. If x equals 1, then there is no change. Now I can integrate, right? So now I have here two integrals, but I will take out only one constant because it doesn't matter, right? Everything can go into this constant. And if I take the exponent of this, I will have 1 minus x equals e to the power of minus half times t plus c. Now this constant can be taken out of the exponent if I define, let's say, c bar equals e to the power of c. Then I have 1 minus x equals c bar e to the power of minus half times t. And here we had the absolute value operator, but we could separate this into cases where the x is larger than 1 and x is smaller than 1, and it doesn't really matter because everything will go into this constant, and we'll change the sign of the constant. So I'm not doing this right now. Now, we find this constant. We can find it if we have an initial condition. If you learned about differential equation, you know that in order to give a full solution for a one-dimensional equation, you will need one initial condition. Two-dimensional equation, you will need two initial conditions, and so on, and so on. So we find this c by having an initial condition x at times t equals 0. For example, it doesn't have to be t equals 0. Equals x 0, and then oh, I forgot to give the final form. So like I said, it doesn't matter that I drop the absolute value because this goes into c. And finally I get x equals 1 minus c bar e to the power of minus c over 2. So x at times 0 is x0 equals 1 minus c bar exponent of minus 2 times 0, and this is just 1. So x0 equals 1 minus c bar, and c bar equals 1 minus x0. So now I have the full solution of this differential equation, and I can even try to plot what happens to the system with time. So we know from the beginning that at x equals 1 there is no change, right? So my ordinate is the x-axis. I can mark x equals 1. If I start at 1, there is no change. If c bar is larger than 1, if x0 is larger than 1, then c bar is negative, right? And here I have x equals 1 plus a decaying exponent. So anything above here will decay into x equals 1. And if x0 is between 0 and 1, I will have 1 minus some decaying exponent. This is a recovery function. And basically it will go like this. And if x0 is negative, then again, it's c is positive, c bar is positive, and this will be why am I confused here? No, you don't have that. Oh, I think I didn't write this in my notebook, so this should also can it be negative? Okay. I don't remember exactly. Yeah, it doesn't matter. Okay, it's the same. It's not a special case. So everything will go into one. Okay, usually you take a break, right? At 10 minutes too? Right. Just to wrap this up, this is a method that you can always use if you have an autonomous equation, and in the exercise you'll be required to solve a few of these. In the next period we will see an easier method, or actually easier tools to solve such equations and even more complicated equations. Not solve them, but get eventually to the qualitative behavior of the system, like I did here, only through an exact solution. Okay, so let's come back at 3.
Can I see what the books are called for this? I don't know if I have access to the new ones because I tried to access it yesterday.
Okay.
So if you give me the book titles, that'd be better.
السكنة ده أنا متجوز شيء
Ja, dat dat is
Can you take your example differential, or your example you developed here?
Summer
כן,
project.
זה שונה קצת.
יש לי כמה שאלות קצת לעקוב. אני עוד לא רשום ואני צריך להחליט אם אני מנה ראשונה זה בעיקרון אמרו לנו שמנחנו נעשה בעיקר בשתי סיבות ראשונות.
כן. לא הכרתי אותך.
לא, כן, אמרו לנו שלפי בעצם
זה היה ממש, אתה ידעת, בגלל זה ידענו
כאילו אני יודע שבהתחיל כל תרגיל
שזה היה נתן
מה אתה
תנאים,
מעריך.
אבל לא ידענו מהם.
אני לא יודע מה
רובנו לא יודעים, אני דווקא ממדעי המחשב פחות כן. אני דווקא ממדעי המחשב רובנו.
כן. התרגילים לא צריכים להיות יותר כבדים מהשיטות.
כי יש לי זמן, כאילו, כי יש לי סמסטר כזה שהולך מעבודה ג'
פחות עבודה מטבעי. שנה שעברה אני עשיתי בטעות איזה עבודה 90.
אז מבין האופציות של כזה קורס נוסף יש לי כן.
Yeah, I don't know if I could find
זה עובד פה?
Oh,
תראה לי איך זה עובד.
במיוחד בשביל
יש לי...
תראה, אז מתי אתה צריך להחליט מה אתה נוסע?
בסוף שבוע. אני חושב גם בגלל שבאמת הסמסטר הזה של השנה הוא קצת...
כן, הוא מאוד עמוס.
גם ניסינו עכשיו את קורס שיטות מחקר הזה.
נכון, שמעתי על זה. תראה, אני חושב שכדאי לקחת את הקורס. זה לא צריך להיות, זה לא אמור להיות עוד קורס של שיטות. זה ממש ישתדל שפשוט אתה תדע לעשות את השיטות. לך ספציפית זה לא צריך להיות קשה. אני לא יודע בדיוק מה להגיד לך. אני חושב שזה מאוד כדאי. גם אתה מקבל קצת יותר ממה שאתה... יש גם ערך מוסף לערך של רשתות.
לא, זה הבנתי שזה כלי שבכל מקרה להשתמש בו.
כן.
שבכל מקרה יהיו לנו. כן, זה אני זה אחת מהסיבות למה אני כן נגד זה. אבל לא יכול להריץ עם זה 3 שעות או 8 שעות לפחות.
מה?
זה תרגיל.
מה איתו?
יש לך תרגיל כמו כל שבועיים. זה תרגיל שייקח לך 3 שעות לפתור.
אלא?
8 שעות תרגיל.
לא אמרת, אבל גם יש לך משוואה מסדר n, פשוט תקבל n משוואות, נגיד לינארית בסדר n, גם n משוואות לינארית בסדר ראשון. אם אני זוכר עוד משהו נגיד יש לך משוואה מסדר גבוה.
כן, והיא לינארית.
כן, אבל לינארית, אתה יכול לקבל
נכון,
n משוואות בסדר ראשון, ואז אתה פותר את כולם.
כן, כן, אבל זהו,
כאילו אין משהו מיוחד בסדר שני מלינארית או בסדר שלישי מלינארית.
היא לינארית.
אין שום דבר מיוחד. כי גם משוואות תנועה של פיזיקה, אז אוקיי, זה משוואה בסדר שני, עכשיו אני אגיד לינארית, לא אכפת לי גם הייתה בסדר שמיני.
נכון.
הייתה חותת באותה צורה.
נכון.
סתם, לא יודע, ככה רשום את הגולמית שלה, לא יודע, נכון?
כן, זה נכון, התופעות שאנחנו מדברים עליהן באות מהחוסר לינאריות, נגיד שלא תקבל סרט עם
כן, כאלה אני לא יודע, כאילו, בסדר.
לא לינאריות, לא רק אחד.
כאילו, אני יודע, ניחושים.
זהו, ניחושים זה באמת,
נלמד פה, כאילו...
אנחנו לא נפתור אותם,
אז מה, כאילו, אז מה
אתה תראה בשיעור הזה.
מה, יוצר את הפתרון במרחב הפאזה?
כן.
איך הם נראים?
צבע שחור, כאילו, רואים את זה טוב טוב.
הבנתי. טוב, זה עולה מיידית או שזה יעלה ככה פעם סמסטר?
אני לא יודע, זה תלוי מי עושה את זה.
הבנתי.
והם יחליפו, אני חושב שהאחראי של שנה שעברה כבר לא אחראי השני.
טוב, סבבה.
שנה שעברה היה מישהו שהכין נוטס במחשב,
שלח
לכולם. אני לא יכול להבטיח שהוא הבין אותו, לא הסתכלתי עליו במחשבה בעיון. אני מאוד מסתיים, אבל אני לא בטוח שהוא הבין לגמרי הכל. אז יש שם בעצם את
זה באתר כאילו?
אבל אני לא יודע איפה זה, אפשר לבקש את זה.
טוב, בסדר. טוב, נפלא.
Okay, so in this period I'm going to introduce the tools that we will be using throughout the semester. Today only for one dimension. So again, our general form is x dot equals the function of x. This is a first order system, of course, and we have no dependence on t. So we would like to given such a system with an explicit definition of f of x, we would like to say what happens to it with time. And we will start by doing an example. X dot equals x times 1 minus x. This is a nonlinear equation, of course. And you can solve this analytically. Okay, you can say that as long as x doesn't equal 0 or 1, then you have g of x, or when you separate the variables, this is what you get. In order to do this, you do a separation into a over x plus b over 1 minus x. And you try to find a and b that will give you that this expression is the same as this one. So for the simplest case, you have a equals b equals 1, and then eventually you arrive at the. Okay, I'll show you this. I'll show this briefly. When you integrate, you get t equals logarithm of x minus logarithm of 1 minus x. And this was for this is in order to be able to do these logarithms and that this will be correct. And you have the constants of the integration, and you can go into this 1 minus x. And you can move the c into the logarithm if you say that c bar c is the logarithm of c bar. Okay, so you have t equals the logarithm of c bar x 1 times x, and then you take the exponent and you solve for x, and what you get is x equals 1 over c minus 1. Okay, so this is a function where you have 1 over a decaying exponent, and you can plot this and see the form that it gives you. For example, if you plot x versus t, if x equals 1, obviously there is no change. I'll do this in another color. If x equals 1, there is no change. If x equals 0, there is no change. And if, well, you need to solve for c bar, but if x is higher, then you go into 1. If x is between 0 and 1, you go into 1 again, and here you have it. You can do the math and substitute and see that this happens. But the point is that this is a nonlinear system. It's kind of difficult to solve it. You have different cases arising from the fact that the integrals of these are logarithms. And you'd like to know how to treat this system simply and also more complex systems. Okay, I won't move the board yet. Okay, an alternative way is what we are going to do in this course. And for this, we kind of go back and try to think about what this equation means. So we have a system of, say, a natural system whose state is described by the variable x, and it evolves with time. So what we have here is an expression for the change in x, basically the velocity in which x changes according to its current value. So if I can imagine the state of the system as a point on the x-axis that can move to the right or to the left, and the velocity of its movement depends on where it is on the x-axis. So this will be x equals 0. And to see the values of the velocities here, the velocities of this point or particle that I imagine, it's useful to plot x dot versus x, and then infer the velocities. So how do I plot this function? X dot equals x times 1 minus x. It's useful to separate this into x minus x squared. So close to 0, this term dominates, and the function looks approximately like x dot equals x. And close to, and when x is very big, then this term dominates, and the function looks like minus x squared in general. So minus x squared. I also know that x dot equals 0 when x equals 0 or when x equals 1. So I can mark this. And basically, this is the form of my function. This is a fast way of plotting such things. So this is the way that x dot depends on x. And what I said earlier is that x dot is just the velocity of my imaginary particle that's running along the x-axis. So I would like to draw this velocity using arrows on the x-axis. here close to 0, the velocity is very small but positive. So I will make a small positive arrow. Here it is a little bigger, so I make the arrow a little bigger. Here it's maximal, and then it becomes small again. So I draw small arrows. Here, just above 1, I have a small and negative velocity, and as x increases, the velocity grows. So I make larger and larger arrowheads. Here, when x is negative, I have negative velocities that are increasing as x becomes more and more negative. Okay, I like to draw this with the arrowheads increasing in size. So already I have a picture of what happens to my particle if I started from here, then I know it will flow into here. If I started from here, it will flow over there. Now, for some definitions that we have, this imaginary particle is called a phase point. Imaginary particle. Just so you'll remember what it refers to. The x-axis is called the phase space. Later, when we have 2 dimensions or more, then the phase space will not be a line, but a plane or a space. Another thing, okay, so what I drew here is called the phase portrait. There will be a few more components to it. And the movement of my phase point along the x-axis, or the phase space, is called a trajectory. Okay, so I don't have a way to draw here, but there is the trajectory. And the trajectory is based at x0. So there can be many trajectories depending on where the point started its voyage. And the trajectory is kind of anchored to this initial point, initial condition. Okay, so we saw that there are 2 special points in our plots, points where x dot equals 0. These points are called fixed points. In short, I will usually write FPs. And the fixed point represents a state of equilibrium, right? If my phase point is located here at x equals 1, it will go nowhere because x dot equals 0. If my point is located at x equals 0, it will also go nowhere because x dot equals 0. These are states of equilibrium. But we would like to further refine our definitions and distinguish between these 2 points. We can see that this is a point that kind of it's a kind of sink for trajectories coming from the right and the left. If I start at x equals 2, my phase point will eventually descend into x equals 1. If I start at x equals 1/2 or 1/4 or 1/10, again, my phase point will descend into x equals 1. This is called, I'll mark it here, this is called a stable fixed point. You can also call it an attractor or a sink. And our convention is to mark it with a filled circle, black circle. this point is different. Trajectories don't go into it. Only if you start exactly at x equals 0, you will remain there forever. If you start at x equals 1/10th or 1,000th, you will go into another place. If you started here, then you will go to minus infinity. This is called an unstable fixed point. It can also be called source, and I think a repeller. We don't really use this term. And the convention is to mark it by a half-filled circle. Okay? What?
The direction of the arrow, you pick it because your knowledge of the system, or is it because of the plus minus?
It's here. Whether x
No,
dot.
how did you make it, from 0 to 1, so it's right, and from,
Because x dot gives me the direction and magnitude of the arrows. So here it's positive, so everything should be positive. And in this section of the axis, it's negative, see? So everything should be negative. All the arrows should point over there. Okay? Usually when you get a dynamical system, you will start from finding the fixed points. Here we went the other way around, and we found them from the curve. But many times, it's obviously easier to solve x dot equals 0. Okay, not always, but a lot of times it's easier to solve x dot equals 0, get x1 star equals 0, x2 star equals 1. And this is the convention for marking equilibrium condition, x star. So an x star can be an unstable fixed point, a stable fixed point. It just means that this is a fixed point, any fixed point. Okay, another comment. The addition of the markings for the fixed point kind of completed the phase portrait. So when you are asked to draw a phase portrait, you need to include in it the axes, x dot, the curve, according to the system that you got, the arrows, and I ask you to draw several arrows in each region to also show the difference in the magnitude, okay? And the fixed points with their classification. All these things make our phase portrait. Okay, so here I explain intuitively the matter of unstable and stable fixed point. If you'd like a more exact definition, it would be that a stable fixed point is a fixed point where every disturbance that is small enough from this fixed point will be dampened. Okay? So if I start at 1 and for some reason the state of the system is brought to 1.1, 1.01, 0.9, anything in the vicinity of 1, and this disturbance will be dampened, meaning that eventually the system will go back to 1, then this is stable fixed point. And you can ask, okay, you say small disturbances, but how do you define how small? So, for example, if the disturbance is very big, you will not go back into 1. Right? So this brings you into another definition, which is that this fixed point is locally stable. Okay? So it's not that any disturbance will bring you back, just small enough disturbances. And for the unstable fixed point, the definition will be that small disturbances from this fixed point will not be dampened and they will take you to a different state. But if you are in this fixed point, you will stay there forever. And I remind you that our systems have no noise in them. Right? If you will stay there forever. Right, so based on the phase portrait, we can go back to the evolution with time and try to see what this system behaves like. So for this, I will make a plot of x versus t. I did a similar plot before. So this will be x equals 1, this is x equals 0. And we will do this plot based on the arrows that we marked. So for initial conditions of x smaller than 0, the derivative with respect to t will first be small and then larger and larger. Small and larger and larger. And if I start here, then I already start with a larger derivative and even larger derivative. So I draw a few courses like this, a few pictures of the evolution with time for different initial conditions for x. If I start above 1, if I'm very close to 1, my derivative will be small from the beginning, and I will go and I will approach 1. Now, since this is an exponential decay, theoretically I will never actually reach x equals 1. Always I'm approaching to a smaller and smaller distance. But we still say that the system descends into this. If I start at 1, like I said, I remain at 1. If the initial condition is a bit higher, then the derivative is a little higher, and so on and so on. Everything decays into 1. Now, this range should be treated a little more carefully. If I start close to 1, then my derivative is very small but positive. So you see this line, it's not steep at all. And if I have smaller x0, then the derivative is a little larger. But there is some maximum point here. So if I start at this area, my derivatives are small. Right? If I start very close to 0, my derivative is very small. But gradually it increases and then decreases again. So I have this sigmoid shape. Something like this. So this is something you will also need to do, to draw the evolution with time based on the vector field that you have here, the velocities of the phase point. Yeah? Question? Yeah.
So how do you know that it gets bigger and it's a sigmoid and not just a very slow rise?
Because as the system evolves with time, say I started x equals 0.1, I have a small derivative, but with time I get to x equals 0.4, 0.5, here I have a large derivative. And only then it becomes small again.
But in the second order, it doesn't necessarily that when the derivative is 0, then you stop. You continue because of the second derivative.
Yeah, a second order system is something else. Usually when we say trajectory, we refer to a trajectory here. Here it's on the x-axis, but when we are in two dimensions, then we have a trajectory on a plane. This is, you can call it a trajectory, but don't be confused. Usually when I say a trajectory, I will mean that. We'll do another example, a bit more challenging. Okay, this is our plot from the analytical solution.
So arrows over there have no meaning, right?
What? Excuse me?
The 3 arrows.
No, they just
They have
no.
no meaning.
Just mean that it continues over there. Maybe I should have put them at the end. Okay, another example that will be very useful for you if you're in the RCMC. This is our system. X dot equals x plus 1 over 2. Now, like I said, the first thing you do when you get a dynamical system is try to find its fixed points. This would mean setting this whole thing to 0 and trying to solve for x. But you cannot solve analytically for x when you have a mixture of linear terms and exponential terms, or sinusoidal terms, or logarithms. So it's not possible to solve analytically for x here. You can do it numerically, maybe, approximate a solution. But I'll show you that we can do things in order to say things, to know the evolution of the system with time without solving for x and without even knowing where exactly the fixed point is. So I'd like you to note that here we have two components, and x dot equals 0 when this, I'll call it f1 of x, is equal to this, f2 of x. So basically I have x dot equals f of x equals f1 of x minus f2 of x. I would like to plot f1 and f2 on the same axis. So I'll call it the y-axis. Now don't get confused. This will not be a phase portrait. This is just plotting these two components. So the first component is just a line. It intersects the y-axis at y equals 1/2. And it has a slope of 1/2. So I'll use colors. This is f1 of x. The other component, f2 of x, we will try to plot based on what happens to it in infinity or at 0. So when x equals 0, then f2 of x equals 1/2. When x is very big, this is 0, and f2 of x equals 1. So I can draw here this asymptote that it approaches. when x is very negative, then f2 of x is approaching 0. Okay, so this would be e to the minus infinity, e to the power of an infinite number. The 1 is negligible, and 1 over an infinite number will approach 0. So also here. This is, in fact, a sigmoid function. There. This is a sigmoid function. All right. Sorry. I drew the slope wrong. It's very important here. Okay. If we want to get the slope, we will have to do f dot 2 of x. We'll have to and you can check me. And at x equals 0, we minus 1 plus minus squared. 1/4. Okay. Sorry, I have to check this before. There. 10 over 4. This is what I wanted. So there are 3 places where these 2 components of our function meet. And at these 3 places, we'll have x dot equals 0. So these are our 3 fixed points. So we'll try to draw a phase portrait based on what we know from here. Now my coordinate is x dot. So x dot is basically the difference between the line and the sigmoid. So let's mark this point here. Okay, we'll mark the point by some indices. So here we'll have x star 1, this will be x star 2, and this will be x star 3. Yeah. So at x star 3, I have a fixed point. I don't know its stability yet. Just above it, x dot is positive because the line is above the sigmoid. Right? So here I have a positive x dot. It grows almost linearly. Similarly, I have a fixed point at x1 star, and below x1 star, the derivative is negative. The line is below the sigmoid. At this area, between x2 and x3, the sigmoid is above the line. So x dot will be negative. And at this area, the line is higher, so x dot will be positive. This is the curve that it would have been quite hard to plot if I had tried this. So now I can draw the vector field. I'll do it in red like I did before. So here I have positive derivatives increasing and increasing. At this part I have negative derivatives. And now I'll take this part with the positive derivatives that have different magnitudes along this range. And here with a negative derivative. This is large. Okay. So now I have a picture of what happens to the system from any initial condition that I will take. And I can also classify the fixed points, right? So things run away from this fixed point. So it's unstable. I leave it empty. Things go into this fixed point. So it's stable, and I fill it in black. And this is again unstable. Okay? So I have one stable fixed point and two unstable fixed points. And I can try to draw the evolution with time. This will be t, this will be x, and I have x star 2, and 3 and 1. As we said before, if you start on a fixed point, you remain on the fixed point. So I'll draw these lines first. Three fixed points. And here, above x3, the derivatives are small at first, but then they increase. Below x1, the derivatives are negative. Yeah?
How do we get to the if 2 equals 0? Let's say you add the 10 over there, it doesn't come up 0.
10 over 2. Oh, I'm sorry. Okay. Yes, you're right. So what was needed here, my correction was bad. Sorry. If I do this.
Yeah, that's
Okay, so now we take this part here between x2 and x3.
Slope.
What?
You change it to slope, so
The slope?
yeah, sigmoid, right?
Yeah, this changed the slope without shifting the sigmoid. Yeah. Does it work? Do you think it should work?
I don't know if you get for sure like x1 star and x2 stars if you
Oh, you must get them
if you should.
because you still have the asymptote at 1.
Yeah, it might go just below the below the f1 f2x might go below f1x all the way.
All the way.
And then
No,
you
but
don't get x3 star.
but the slope here is 10/4 instead of 1/2.
Now it's 4 when you change it back to 1.
No, when you change exponent.
I check.
Get the 10 out.
Yeah. So here this goes out. Okay. Okay. So in this range, if we start next to the stable point, we have small valued derivatives. If we start next to the unstable point, they are small, but they increase in their value. So we get the sigmoids again. So these are not sigmoid, but here we have sigmoids. And again here. So this is the way our system evolves with time, depending on where it starts. If you start within this range, you will go into x equals 0, either in an exponential decay or in this sigmoidal fashion. If you start here, you will go to infinity. So you get 3 fixed points here. Now, the important point about this example is that we were not able to find the fixed points analytically. We just inferred their existence and the approximate range of where they are. And then we were able to say what the system does with time without knowing exactly where the fixed points are. So this is quite good, getting this dynamical system and still being able, without solving the differential equation and without even setting it to 0 to find the fixed points, to know what happens here and to make some predictions. In the next lesson, we will see a more exact method to classify the fixed points. Here I just said, the arrows go into it or the arrows go out of it, so it's stable or it's unstable. So we'll see a more formal definition. And we will also look at an applied model. So we'll do these same things for our system where the variables and the parameters represent physical quantities. It will be a model of a population. And we'll also learn about numerical integration. So you will be able to run simulations of such dynamical systems, either one-dimensional, two-dimensional, three-dimensional. And there are some points that you need to know about the way that you integrate them over time. That will be covered in the next lesson. About the exercise, I will try to post it today, and it will be due for 2 weeks from now, okay, the beginning of the lesson, covering this and also the next class.
Do you have published notes?
No. Oh, I forgot this.
אתם יכולים להדגים את